Okay, a very good morning to all of you. Welcome to this morning's class. I should state at the outset that today we have a slightly bigger class because the students of the MSc third year who have taken their special paper in astronomy and astrophysics are also there with us. Unfortunately, the semester has been quite delayed and they have just started. So I'll be teaching them during the week as well, but they will be attending the Saturday classes as well in order to catch up with all that has happened or has been done. Now, today we will talk about estimation of mass in our series of discussions on estimation of physical properties of celestial objects. Okay, and let me sort of first try and ask you, what are the different ways you think you can estimate mass of celestial objects? Any one of you can unmute and share your thoughts.
Seeing the effect of their gravity on other objects.
Okay, but a bit more precise than that. I mean, that is a very, very general statement.
So along those lines, like say you have like a star of a known mass that based on the orbits of other bodies around it, you could figure out the masses of the other bodies.
Okay. I would like others to also contribute besides Ahan and Apino. Anything else that you can think about?
Curvature of light around the object.
Curvature of light around the object. Very good.
It's studying the density of different elements through the emission spectrum.
Excellent, Kriti. That is also being done, particularly in case of smaller bodies. Okay. So you'll have covered essentially some of the basic ways that one tries to measure mass. One is when you talk about motion of one object around another, is application of Kepler's laws of motion. And one does much more detailed calculations in terms of looking at effects of other bodies as well, while trying to get very accurate masses. But for our discussions, we will keep it at the basic and simple level. Then there is the application of the virial theorem, which relates the potential and kinetic energy of a system. Okay, and the potential energy would be related to the mass, the kinetic energy related to the velocities. And if you can estimate the velocities, you can try and get an estimate of the mass. And gravitation lensing, which Pratap mentioned about bending of light. So the degree of bending will depend upon the mass, the distribution of mass. The detailed images will depend upon that. And then also rough estimates from density and the volume, which Kriti mentioned, that will also give you an estimate of the mass of an object. But often it's, for very massive objects, it's a bit difficult, but for smaller bodies, it is something which you can do. But even when that was done, there were surprises when they had got more accurate estimates. And we will probably see one of the examples of that kind. Now, bodies moving about one another, one can use to estimate the mass of objects in our planetary system. And as you said, the sun, one can look at the motion of the Earth around it and try and get the motion, an estimate of the mass of the sun. So we'll just go through this rapidly because this is something which you're familiar with. Now, for example, sun, if I just equate the gravitational to the centripetal force and just use a very simple form of it, and use the gravitational constant, the average distance between the sun and the Earth, which is 1 astronomical unit, I can get, but just by plugging in this, I can get a number of 1.99 into 10 to the power of 30 kilograms. And more accurate estimates, because here we have assumed that it's in circular motion around that, but it is not exactly circular. It is also, we've ignored influences of any other bodies on it. But you can see even with these simplifying assumptions, it gives you a reasonably good value. Similarly, you can use the motion of the moon around the Earth to estimate mass of the Earth, or motion of satellites orbiting the Earth to mass of the Earth. So mass of the Earth, the accurate value is 5.973 10 to the power of 27 kilograms. So you can see it's roughly about 3 orders of magnitude less massive than that of the sun. Now, how about the moon? How would you go about estimating the mass of the moon? Anybody would like to sort of just suggest how do you estimate the mass of the moon? Similar argument.
You could see perhaps the strength of the tides on the Earth, or how it gravitationally affects the Earth, the wobble it induces in the Earth.
It would, I mean, there's simpler ways of doing it. You could model that perhaps. Well, we have things going around the moon, right? This is just a crude estimate again from this is the Apollo 11 command module, which is going around the moon while Neil Armstrong was landing on the moon and his colleague. Okay. Now, what I've done over here is I've just taken some parameters of the average distance between the Apollo 11 command module and a rough period of about 2, and plugged it into the same equation, and I get a number of about 5.97 into 10 to the power of 22 kilograms. A more accurate value would be 7.353 10 to the power of 22 kilograms. So you can see it is much smaller, and this accurate value allows for influence of Earth's gravity, and also, a more accurate period will give you a better value. What about now Jupiter and planets with moons? You can use a similar method because you have a moon going around planets with moons. Now, what about planets without moons? Mercury and Venus. How do you go about it? Again, you have to rely on the gravitational influences of other bodies. This is, I just picked up 2 papers to illustrate to you the kind of exercises that people have done to find out the masses of planets without moons, such as Mercury and Venus. Okay, this is from the Polish group from the Space Research Center in Warsaw, and they looked at the motions of 5 minor planets or asteroids over a long period of time. They monitored its motions, and the mathematics is more complicated, and they arrived at accurate masses of Mercury and Venus. Here they have given it in terms of inverse of the solar masses, but if you look at it in terms of just kilograms and what fraction or how many times heavier than the mass of the Earth, then you'll find mass of Mercury to be 3.285 into the power of 23. Venus is slightly heavier by about an order of magnitude, and this is in terms of the fraction of the mass of the Earth. So people have looked at the masses of Mercury and Venus by looking at the masses of motion of asteroids. Now, how would you get the masses of asteroids? Now, the bigger asteroids, for example, Ceres and Vesta are 2 of the more massive asteroids. They're designated as minor planets. Ceres was discovered in 1801 by Giuseppe Piazzi at the Palermo Astronomical Observatory. And Vesta was the 2nd largest asteroid after Ceres and discovered in 1807. So you can see this is early part of the 19th century that these were discovered. Now, what they have looked at is, well, these are some of the much bigger asteroids, okay? Much bigger asteroids. And they have monitored the motions of a variety of asteroids, which would be sort of gravitationally interacting with them. So I can see, you can look at the abstract of their paper over here. They solved, correspond 26 normal equations corresponding to 1536 observational equations, etc., and arrived at the masses of these asteroids. Very small objects, you have to get smaller asteroids. I think Kriti mentioned that some estimate of what it is likely to be made up of, and from the density and the volume, you'll have to try and get an estimate of the mass of the smaller objects. But you can see that gravitational influences play a major role in terms of trying to get information on the mass or estimates of mass of a variety of objects, right from stars to asteroids. This one, I just want to mention 1 or 2 things that, we mentioned about picking up material particles by spacecrafts from orbits in terms of getting information from material particles as part of our series of lectures or discussions on multi-messenger astronomy. Here is just Sirius and Vesta, which I talked about. NASA's Dawn satellite, which was, I think, launched in 2007, went into orbit around Vesta in 2011, and then went into orbit around Sirius in 2015. So it was the same mission which orbited actually two of the minor planets, two of the big asteroids in our system. And these are the approximate distances from them. And they brought back absolutely stunning pictures and a lot of information on these two minor planets or asteroids. On the left, you can see a pitted terrain on the floors of the craters, two of the craters on the minor planet or the big asteroid Vesta. Middle shows evidences of landslides, which is possibly shaped by water ice. And in one of the craters, which is sort of indicated in red, there seems to be evidence of organic material as well. And it would be interesting to sort of explore, understand the origin of life, to look at the organic material which may be present and how they may relate to organic material which we know on the Earth, to get a better grip on how life may have originated. This is another sort of illustration of some of the space missions. This is a much earlier NASA's mission near Shoemaker, which flew by asteroid 253 Matilda on way to asteroid 433 Eros. So these are the tracks actually over here show the satellite, and the Earth has a blue orbit over here. The yellow is the sun, and in green is Eros, and light blue is Matilda. So from the flybys, because these are, if you're going to shoot rockets out, then obviously the orbit is going to change due to the propulsion by the rockets. But on the other hand, if it is just following a path due to the force of gravity, you can use that to estimate masses of celestial objects. So this is just another example of it. So in terms of our solar system, we found that by looking at the motions of objects, one can try and get estimates of the masses of these objects. Now, when you want to do a more exact formulation, rather than just equating gravitational and centrifugal force, one has to look at not only Kepler's laws of motion, which we will do in a short while, but also the perturbative effects of other systems which may be nearby. So I would just want you to be aware of that. We will not deal with those equations in this course. But Kepler's first law, you'd have read it as the Earth moving around the sun, with the sun at one focus of the ellipse, and the Earth has an elliptical motion. Ellipticity is small, but it is still elliptical, as several of you have pointed out or discussed during the course of these lectures. So this actually gives you the figure of an ellipse, and this on the upper equation is the equation of a conic section, where L is the angular momentum, mu, small mu is a reduced mass, 1 upon mu would be equal to 1 upon m1 plus 1 upon m2, and capital M is equal to m1 plus m2, the masses of these two objects. And for an elliptical motion, R is equal to A into 1 minus E squared divided by 1 plus E cos of theta. Now, if ellipticity is zero, you can get A over here, and it should also be 0. So R is equal to A. So ellipticity of 0, you'd get back a circle. So basically, the part of the reduced mass about the center of mass under inverse square forces is a conic section. So if you take a cone and take a slice through it, it could be an ellipse, it could be a circle, it could be a parabola, it could be a hyperbola. Okay. Now, Kepler's second law of motion tells you that the line joining a planet to the focus sweeps out equal areas in equal intervals of time. The derivation of Kepler's laws of motion is given in Carolyn Osley's book. For the MSc batch, we will try to derive it later, but for the IDSS students, it is enough to just right now be aware of the second law of motion, and dA dt, that is the rate of change of area, is given by half capital L, which is angular momentum, and mu is a reduced mass, which I just said is 1 upon mu is equal to 1 upon m1 plus 1 upon m2. And because L is a conserved quantity and a mass assumed to be a constant, so you'll have dA dt is equal to constant. So the line joining a planet to the focus sweeps out equal areas in equal intervals of time. Kepler's third law says that P is equal to Ka cubed, okay? Now, when but when you actually need to derive it properly, you'll get P squared is equal to 4 pi squared divided by G into m1 plus m2 multiplied by A cubed. So P squared is proportional to A cubed, and the constant of proportionality is 1 upon G, the 4 pi squared upon G into m1 plus m2. So you can see that P squared is proportional to 1 upon m1 plus m2. Now, if the mass of a planet can be ignored, which is a much smaller fraction, as you saw, of the mass of the sun usually, and so you can just have it as the mass of the sun over here, for example. Now, you can see from this equation that if I were to put P, the period in years and the semi-major axis in astronomical units, so the average distance between the sun and the Earth is 1 AU, and the period is 1 year. So if I were to express this in terms of years and astronomical units, then the constant K is equal to 1. Okay. Actually, Kepler, when he formulated this law, did not quite realize that there was an inverse dependence of the mass of the sun plus the mass of the planet. But the fact that the mass of the planet is so small, it did not make any significant effect on the plot which he made. But when we talk about different systems, we have to bear this in mind, okay? That P squared is inversely proportional to the sum of the masses of the two objects, okay? Now, because this is applicable to the Earth, but it's a very general formulation. So as far as the mass of the sun dominates, for all the objects in all the planets orbiting the sun, you will get P squared is equal to A cubed with K equal to 1. So you can verify this for yourself as well. But what I've done is I've just shown it briefly over here and listed the semi-major axis. Don't worry about the eccentricity right now, and the orbital period, okay? And you can calculate P squared upon A cubed, and I've just done this over here, and you can see within the errors, they're all consistent with being 1, right? So that is Kepler's laws when applied to the solar system, with our planets moving around the sun. Now, what about moon and the moons of Jupiter? What do you think would be the ratio of P squared upon A cubed? Okay. Would it be larger, smaller? Would it be 1? What do you think would be P squared upon A cubed for a satellite orbiting the moon, or the moons of Jupiter, which are orbiting Jupiter? No? Okay, you have to remember that is inversely proportional to the mass. Okay, P squared is equal to 4 pi squared upon G into m1 plus m2 A cubed. It is only when we put the mass of the sun over here, okay, for our planetary system, P squared is equal to A cubed. So for example, the Earth going around the sun, period is 1 year, average distance is 1 astronomical unit, P squared upon A cubed is equal to 1. When you talk about the moon going around the Earth, okay, then what is happening is that what is going to enter at the bottom part of this equation is not the mass of the sun, but the mass of the Earth. Okay, mass of the Earth plus the moon. But again, we are taking this right now as an isolated system. If you want to do more accurate calculations, you'll have to take account of other perturbative effects as well. But right now, we're just looking at the Earth moon as an isolated system. So P squared upon A cubed is going to be pretty large. That's what you find over here. You can check these numbers on your own. I just sort of did it rapidly while trying to prepare these slides. Now, if I take Jupiter, for example, okay, Jupiter, and this is one of the satellites orbiting Jupiter. Now, you can see that Jupiter is much more massive than the Earth, isn't it? Okay, it's about 3 orders of magnitude more massive than the Earth, whereas the Earth is about 3 orders of magnitude less massive, but the Earth is about 6 orders of magnitude less massive than the Sun. So because Jupiter is more massive, you'll get p squared upon a cubed, which is larger than 1 clearly, because Jupiter is much more massive than the Earth, but much less massive than the Sun. So you get a number which is in between. Okay. Now, what do you think will happen to comets? If I look at the orbit of a comet, say in an elliptical orbit, what would be p squared upon a cubed? No?
Sir, I'm not sure about p square upon a cube, but I know for Halley's Comet, the period is 75 years after when it comes in near the vicinity of Earth.
Okay. Okay. Thank you, Kamakshi. Yeah. But the thing is that what you have to look at is this equation, which I want you to sort of understand properly. Okay. This comes from Kepler's laws of motion. All right. Now you see that when the motion is governed by the motion of the sun, okay, when you have, and that is true of the planets, then you have this p squared upon a cubed, which is effectively this constant, is unity, because the Earth has a period of 1 year and a distance of 1 astronomical unit. And we just saw that for all the planets, if you look at the period and the AU, because this is the general form and the only thing which is changing is are the periods and the semi-major axis, but this constant is just a constant, which is the mass of the sun. So when the comets arrive, right, they are orbiting the sun. I mean, they may be perturbed by the planets, but basically it is the sun which is governing their motion. So here again, anything for which the sun is governing the motion, you will get this constant to be 1. So p squared is equal to a cube for the planets, for any object which is orbiting the sun, because the mass term which comes here to a reasonable degree of accuracy, whether it be even for a planet, it's m sun, but for a comet, it would be, the mass would be minuscule actually. So you can put m sun over here and you will get equal to 1. So p squared upon a cube is equal to 1. Okay, Abhishek, do I have to unmute you? You can unmute yourself and ask your question. You put your hand up, Abhishek.
Sir, we are looking at the ratio of p squared by a cube. It's nearly about 1 or so. So what it signifies basically the ratio? I mean, physically, what it signifies? I mean, we are interested in finding out these.
What is? This is physically what it signifies is the mass of the central object that is governing the motion. Okay. If it is the mass of the sun which is governing the motion, you get a number which is 1. Okay, as long as you also express the semi-major axis in astronomical units. So any object with the mass of the sun, the period expressed in years, and the semi-major axis expressed in AUs, the proportionally constant would be 1. So physically, what this is telling you is the mass of the body which is responsible for motion around the object. Okay. So that is what it gives you an idea about. All right. Now, this is what I've written down for comets. Okay. For a few select comets, you can see eccentricities vary quite a bit. And from Kepler's laws, you can find out the distance of closest approach to the sun, perihelion and aphelion. But you can see, because it doesn't really depend very much to a first order, because we have not taken that into account. To first order, you can see, if you can ignore the mass of the orbiting object, that p squared upon a cube is equal to 1. So it basically tells you the mass, physically, the mass of the object which is responsible for the motion. So any object which is orbiting the sun, or an object which has the same mass as the sun, and you express the period in years and the semi-major axis in astronomical units, that constant would be equal to 1. All right. So
Well, why does the p squared divided by a cubed not exactly equal 1 in this case? Because the mass of the comets is insignificant.
The comets would be also prone to perturbative effects of other planets. So within the errors of measurement plus the perturbative effects of other planets, you are not getting a number which is identically 1, but it is close to 1. And you can see over here that of the 3 comets which I've mentioned over here, 3 of them actually come pretty close to the sun. This one, 1943.1, is almost a grazing incidence to the sun. And so they are less than 1 astronomical unit at its distance of closest approach. Okay, now we will try to extend this to the studies of binary stars. Okay, we have mentioned already in earlier that stars are rarely single objects. Okay, the bulk of them occur in multiple systems. 2 or more stars, about 80% of stars occur in binary or stellar systems. This perhaps has to do with the way they have formed from the condensation of giant molecular clouds. In very dense stellar systems, there could also be capture of stars in its vicinity. But usually, as we saw, that except in very dense stellar systems like globular clusters, that the volume of occupied by stars is minuscule actually. Okay, we did this some earlier on, but for this class, it's important to just realize that the bulk of the stars are in multiple systems consisting of 2 or more stars, and we will try and look at a simple situation of trying to estimate the mass of stars using Kepler's laws. But while trying to do that, we will just briefly mention about the 4 main types of binary stellar systems. There could be a star which appears very close to one another, okay, and but they are actually very far away, because whenever you look at the sky, you're seeing everything projected onto the plane of the sky. So those are not the binary systems that we're talking about. We're talking about binary systems which are gravitationally bound or under the influence of one another. So they're visual binaries, not necessarily visual to your eye, but at least with a telescope, you can make out that they are 2 different stars which are orbiting about each other with the resolution of the instrument that appear to be 2 separate stars. Then there could be spectroscopic binaries, which means that you cannot separate the 2 stars. You may not be able to separate the 2 stars, but you can see the shift in the velocities of the absorption lines as the 2 stars orbit each other about the center of mass of the system. Okay. Then there could be eclipsing binaries, where one star comes in front of the other. That means their orbit is inclined at an angle such that the orbit of one star, when it is orbiting, comes in front of the other and it gets eclipsed. Then there are astrometric binaries, where from slight positional shifts, you may be able to infer that there is another star which may be below your detection limit, but for the one which you can see from the systematic change in the position as it is orbiting about the center of mass of the system, you may be able to infer that this too is a binary system. So as I said, 2 stars just appearing close together but not physically associated is what is often referred to as the apparent binary. Okay, and I should say that these are not mutually exclusive. For example, a visual binary which you can separate out, it may also be a spectroscopic binary. For example, you can see the Doppler shifts in the lines quite easily. While seeing the Doppler shifts of the lines, one should mention that if the stellar system, if the orbit is exactly on the sky plane, which means it's perpendicular to you, then you won't be able to see the shift in the lines, because what you measure are the radial velocities. And if it is moving in a direction which is orthogonal to you, then you will not be able to see it. Similarly, a spectroscopic binary may also be an eclipsing binary. So these are not mutually exclusive, but these are the 4 main categories to keep in mind. So you can see over here, this is just a file showing 2 stars orbiting about the center mass of the system. One smaller, one bigger. And an example of a visual binary system which is resolved by the Hubble Space Telescope is Alpha Centaurus. We talked about Proxima Centauri being part of the Alpha Centauri system, which is the nearest star. And Alpha Centauri A and B are just a bit further away. And this is an HST image of it resolving the two stars. So this is an example of a visual binary. This is an example of a spectroscopic binary. So we have mentioned earlier that, and we will study it in a bit more detail when we discuss stars, that these spectroscopic binaries are ones where you see the shift in the absorption lines, and stars, as we mentioned earlier, are characterized by absorption lines. Some exotic stars also have emission lines, and these stars may not be resolved, but a binary nature can be inferred from the systematic shift in the spectral lines as they orbit about each other. So Mizar was seen as a visual binary by Giovanni Riccoli in 1650. The spectroscopic shifts was noticed much later, okay? And even Mizar A was actually again resolved into individual stars. This is the optical interferometer at Arizona, and Mizar B was found to be a spectroscopic binary. So you can see these stars can be multiple systems, and one can, if one has to deal or understand it in detail, one has to understand all the components which may be influencing its motion. Eclipsing binary is where one star comes in front of the other. So the way you can make out is that the amount of light from the system will keep changing periodically as one star eclipses the other. So usually one sees 2 dips in brightness, the primary eclipse as it's called, and the secondary eclipse. And most good mass estimates actually have come from eclipsing binaries traditionally, but today there are also pretty good algorithms which try to infer the orientation of the orbit, which, as we shall see, is an important parameter while trying to estimate masses of these objects. And if the orbits are too close to each other, they could tidally distort each other as well. So the detailed light curve, how sharp it is, whether it is flat at the bottom, and the nature will depend upon the inclination as well as distortion of the binaries by each other's tidal interactions with it. And also stars may have atmospheres, so atmospheres may also soften the edges rather than have very sharp edges over there. Okay. These are just sort of secondary effects to be kept in mind. So can you sort of say what is the reason for a primary eclipse and a secondary eclipse? Any ideas on that?
The primary eclipse is the greatest drop in brightness, so it's the brighter star behind the dimmer star. And the secondary eclipse is a lower drop in brightness, so it's the brighter star in front of the dimmer star.
Okay. Does anybody else want to agree or disagree with Aquino? Okay. Okay. So basically, I'm illustrating the same thing to you with 2 stars over here. One is with a temperature of 5,800 K, the other with a temperature of 4,140 Kelvin. Okay. Now, the total luminosity from the star will also depend not just on the temperature, but also on the radius of the star, right? We learned from Stefan Boltzmann's law that stars, the luminosity of the star can be approximately given by L is equal to 4 pi r squared sigma t to the power of 4. So both the radius and the temperature will play a role, but the basic idea is that when the hot star is being eclipsed, or the one which is more luminous, okay, because the temperature dependence is stronger, so more then you will get a deeper drop over here. And here you can see the secondary eclipse where the cool star is being eclipsed. Okay. So these are the examples of eclipsing binaries. And eclipsing binaries, you can assume it to be close to the plane to be perpendicular or along the line of sight. Okay, so that the orthogonal to the plane is on the sky plane. And even if it is slightly off, the errors which you get would not be huge. But today there are pretty good methods of trying to determine the inclination. So this is what I meant by astrometric binaries. A binary system in white star may not be visible, but shows a wobble due to the gravitational influence of unseen companion. Sirius A is a bright star. Today we can see both, but in the early days, the dimmer white dwarf companion Sirius B was inferred from the wobble which Sirius A exhibited. Okay? This just shows you the wobble as one observed the system from 1910 to about 1980 or so, right? Today, actually, with these space telescopes, the high resolutions that one is getting, that one is being able to resolve many of these nearby binary systems. In addition to these types of binaries which I mentioned, there are also very exotic binary systems like the binary pulsar system, which is I've just listed away the first known binary pulsar system, where one has a 23 millisecond pulsar period, and the other one rotates once every 2.8 seconds, and the orbital period is 2.4 hours. It is also an eclipsing binary. So a lot of interesting information have been garnered from this particular system. And there are also X-rays, as we learned while we were looking at the X-ray universe, that there are binary systems where one may accrete matter from a companion star and emit at high energies. So these are very exotic systems, but and they are it's studied extensively at X-ray wavelengths and part of high energy astrophysics. The emission processes, the generation of these high energy photons, heating of the gas to such high temperatures, etc. Now, let's try and just have a look at the steps into what trying to estimate the mass of a binary system. Okay. Now, this is what we wrote down as Kepler's law. P squared is equal to 4 pi squared upon gm1 plus m2 a cubed. I could reverse this equation to write down as m1 plus m2, 4 pi squared upon g a cubed upon p squared. So if I know the semi-major axis and I know the period, I can straight away get the sum of the masses of the two objects, m1 plus m2. Okay? But we would also like to know the individual masses of the objects, m1 and m2. And for a binary system with both moving around the center of mass, around the very center, m1 d1 equal to m2 d2, which will give you the ratio of the masses, m1 by m2 equal to d2 by d1. Now, I've largely taken this from Carroll and Osley's book, which all of you have or have access to, and I'll anyway share the slides. So right now, just follow the arguments, and a more detailed derivation of these equations is given in Carroll and Osley as well, so you can follow it later. More detailed derivation of Kepler's laws is also given in Carroll and Osley, which you can sort of look up later. Okay. Now, from these equations provides a means of estimating stellar masses from binary systems. Okay. So we have the ratio of the masses from here, and we have the sum of the masses from here. And the semi-major axis is equal to d1, d2, the separation of the two objects from the center of mass of the system. Okay. Now you could do a bit of substitution, and using these equations, you can, using these two equations with a little bit of algebra, you can get an expression for the masses of the individual stars as well. M1 equal to is given by d2 upon d1 plus d2, and for M2 it's equal to d1 upon d1 plus d2. You can do this as a small assignment, and it's very straightforward and simple algebra. Now, let's look at visual binaries to start with. Some of the material I'll keep repeating from slide to slide, and we will take the orbital plane perpendicular to the line of sight. Okay, and m1 upon m2, as we just saw, is d2 by d1. Actually, different books use different sort of different symbols for it. So I put all the common symbols which are used. Caroline also uses A. D2 is also used, R2 is also used. So basically, it's a distance from the center of mass of the object. I've used capital D for the distance to the object. Okay? So if I have a visual binary where I can resolve the two stars, I can actually, even if I don't know the distance, I can know the angle of separation. Okay, alpha 1 is equal to A1, the actual separation, divided by D. And these are small angles, so I can use a small angle approximation, in which case I can express M1 by M2 is equal to alpha 2 by alpha 1. So I can get a mass ratio from the subtended angles, even if I don't know the distance to the object. Okay. In a general Kepler problem, A is equal to A1 plus A2. So then the distance would be required. But just to get the ratio of the masses of a binary system, I can do with measuring the angles as well. Now provides the means, okay, of estimating stellar masses. So I just expressed this as M1 by M2 instead of D1 by D2 or A1 by A2. I put it as M1 by M2 in terms of the angles, okay? In terms of the angles. And what you have to realize is that the orbit may not be at the plane of the sky, okay? Suppose it is not at the plane of the sky, then I have to look at the angle of inclination of the orbit to the sky plane. And that is given by this angle I, okay? That is given by the angle I. This is the plane of the sky, and this is the plane of the ellipse over here, and the angle of inclination is equal to I, okay? So if I is 0, cos 0 is 1, and so you just get back the standard equation, which you're more familiar with, okay? Now, usually measuring I is a little bit of a challenge, but it's possible. So this actually gives you an estimate of M1 plus M2, if you can make a guess about I, and if it is, as I said, if it is in the sky plane, I is equal to 0 degrees, cos 0 is equal to 1, and this gives you the ratio of the masses of the objects. Now, this is what you can do for the visual binaries, and from that you can go and get an estimate of the masses of the objects. Now, the inclination will also affect the star's radial velocity values. Radial velocity will be maximum when the plane of the orbit is along the line of sight, that is I is equal to 90 degrees. But I is equal to 90 degrees, but when I is equal to 90 degrees, you effectively get an eclipsing binary, right? Because one will go in front of the other as well. And for an object on the sky plane, as I said, I is equal to degrees. So you're not going to measure any radial velocity. Sine 0 is 0. Otherwise, the maximum value of V1 for the two components which are orbiting about each other would be V1 R max is equal to V1 sine I, where I is the angle of inclination of the plane to the orbital plane to the sky plane. Okay, so you can see from here that if I just do again for circular or orbits, eccentricities are usually small. So if I just assume circular orbits, I can put velocity of one star as 2 pi a1 by p, and velocity of the second star as 2 pi a2 upon p. This is nothing but v equal to r omega, right? Which you're familiar with from your classical mechanics. Omega is 2 pi nu, so that's where 2 pi comes from, and nu is equal to 1 upon p, all right? And m1 by m2, we saw that when they are orbiting about the center of mass is equal to a2 by a1, which will give you the velocities over here, and then you can divide by sine I to get velocities in terms of what you measure, because v2 would be equal to v2r divided by sine I, okay? And sine A will cancel, so this will give you v2r by p1r. So again, over here for ratio of masses, we do not need inclination as in the case of visual binaries, okay? If direction of motion perpendicular line of the site, radial velocity is 0, okay? That we have sort of mentioned earlier as well. So these give you estimates of the masses. Now, I've just done a little bit more algebra over here to put the sum of the masses, m1 plus m2, in terms of the period and the radial velocities which you measure. And then because of the inclination and dependence of that on the sine of the angle, you will get a sine cube I term over here. So you can see that if your I is uncertain, because it's a cube of it over here, that you'll have significant uncertainties in terms of the masses of the objects. So it is good to be able to determine the mass of the angle of inclination as reliably as possible. And in the case of Eclipsman binaries, it is sort of more easily done. But in case of others also, as I said, that you can make reasonably good estimates. Okay. So you have the ratio of the masses and you have the sum of the masses, which we have seen for spectroscopic binaries as well as visual binaries. Now, what I wanted to point out over here is that sometimes what might happen is that one star is pretty weak, okay? You only see the binary spectra from one star. It's a single line binary system. You don't see both the lines. In a spectrum of star 1 is available, but not of star 2. Star 2 is too weak and you're not able to detect the spectral lines. Then you can again go back over here and express it in terms of the ratio of the masses over here. And this again, I'm not doing the algebra in detail, but I'll give it as an assignment. So maybe later, if you're unable to do it, we will do it in one of the classes or tutorial sessions. Okay. So even from the measurements of one star, you can go and get what is this mass function, which is a function of the masses of the two stars. Okay. That is something which you can determine and put limits on the mass function, depending on the angle of inclination of the object. Now we will just do a few sums to illustrate that using the Alpha Centauri system, okay, in terms of using Kepler's laws for estimating masses of stellar objects. Just to recap over here, m1 plus m2 is equal to 4 pi squared upon g, a cubed upon p squared, and m1 d1 is equal to m2 d2, where d1 and d2 are the distances to the center of mass of the system, and this is saying the same thing, and the semi-major axis A is equal to d1 plus d2. Now let us take the Alpha Centauri system itself, which has a period of 79.92 years and a mean separation of 23.7 AU, and the distance is about 1.338 parsecs away from us. Okay, so this is one of the systems where distances, we know this is Proxima Centauri, which is associated with it. It's slightly closer, but this is the nearest stellar system. So to calculate it, I need to express everything in a similar unit. So if I want to use the SI or the MK as units, I need meters and seconds. So period 79.92 years, I've converted to seconds. A, I've converted to the semi-major axis, which is given in astronomical units. And as you know, the astronomical unit is the average distance between the sun and the earth. And I convert that into meters. And then I just plug it over here. Okay. And I will get M, which is the mass of the sum of the masses of the two objects. Okay. And sum of the masses of the two objects, you can see it is slightly greater than the mass of the sun. It's about a factor of 2, slightly more than a factor of 2, more massive than the mass of the sun. Now, suppose I want to also know the mass of the individual objects. Okay. Now we have given the mean separation from the from binary system barycenter as 11.2 astronomical units. Now this expression, which gives you M1 in terms of the combined mass of the two stars, which we have just calculated. A is a semi-major axis. D1 is a separation of one of the objects from one of the stars from the central mass of the system. And this has been given as 11.2 AU, which I will again convert to meters. So using this expression, this is again a very simple derivation, which I will give it as an exercise. you can go and calculate M1 is equal to M, which we have just calculated in the earlier slide. And then I can go and put the A over here minus D1. A we calculated in the previous page, A1, which will give me a mass of about 2.2 into 10 to the power of 30 kilograms. So I can, from the parameters which I've given, I can go and estimate the mass of each individual star as well. First, I had a combined mass, and then I've got an estimate for the individual masses as well. M2 is nothing but the total mass divided minus M1, which will give me 1.97. So if you compare with the mass of the sun, you can see that Alpha Centaurus A is similar to that of the sun. It's a G-type star. We have briefly mentioned about spectral classification, but we'll do it in a bit more detail when we discuss stars. And Alpha Centaurus B is slightly less luminous than our sun. It's a K-type star, it's less luminous, and it's dimmer, and it's in the main sequence of stars. So you can see that from applications of Kepler's laws, for this visual binary system, we have been able to estimate the masses of the individual stars. Now, here I've written down another equation, which I'll again give as an exercise because these are simple things which you can work out yourself. But I'm considering a situation now where only a single star is visible. How is that likely to happen? Suppose I had a planet, which I cannot see, but I can monitor the motion of the object, of the star, okay? And notice a slight wobble in it. And can we get an estimate for the mass of the planet, okay? Now, let me define this ratio, gamma, as the ratio of the masses. And again, M1 D1 equal to M2 D2. So this, I'll play around with this equation and get it in terms of gamma, okay? Now, M1 is the mass of the star, okay? And M2 upon M1 is the ratio of the mass of, say, a planet to the mass of the star, right? And if I can measure M1 and D1, if I had good astrometric measurements, I'll be able to measure that. And M1 is a bit of a guess, because M1 I can try and make an intelligent guess if I know what kind of star it is. And what kind of star it is, I can try and estimate from the spectral class of the star and the luminosity class of the star, okay? So I can get an estimate of what the mass of the object is, and these are usually okay to about 20%. So it's not a highly accurate number, but you can see that even from one star, which I can see, I can go and get a reasonable estimate of the mass of the planet. Here it is. Here actually this function has to be single value, which just shows that that is okay. All right. Now I've talked about sort of looking at the motions of stars so far, but this method has its own complications. Complications arise because the stars are not just moving about the center of mass of the system. We are actually moving around as well while you're making these observations from the sun. And also the whole stellar system may be moving, okay? So while doing the final fits, one has to allow for that as well. That not only the orbital motion about the star, because in a real situation, while we're making measurements, we have to take care of parallax, where the apparent position appears to shift because of the Earth's motion around the sun, and also the proper motion of the stellar system itself. The whole binary system may be moving in a particular direction. So one has to look at that. This is just a fit for a particular star, taking care of parallax, which will appear to shift because of the motion of the Earth around the sun, of a more nearby star against a background of more distant stars, and a whole proper motion of the system. This is in coordinate systems of in the sky of right ascension and declination. Things can become even more complicated, and these are just to illustrate to you that when we talk about proper motion of a star, heliocentric parallax, it also depends on how accurately you measure these positions, over what duration you have to make these observations. Some maybe have long binary systems, some may be short duration binary systems. But basically, you have to model these different motions as well in order to try and accurate motions of the masses. Now, I mentioned about inclination angle. So this is just to illustrate to you that obviously when there is an eclipsing binary, it is very close to 90 degrees. May not be exactly 90 degrees, but you can guess, hey, it must be about 80, 70. And then you can calculate what are the uncertainties you have in your number if it varies between about 70 and 90 degrees, say. Okay, but can we do better than that? Can we do better than that in terms of trying to get an inclination angle from the observed path of the ellipse? Now here, for example, if you get a circle and tilt it, you'll get an ellipse. And that is something which usually we are quite familiar with and it sticks to our mind. But if you tilt an ellipse also, you can get a circle, all right? So one has to be a bit careful while trying to infer inclinations from the observed shape of the orbit. But if you time it in a very regular interval, then you can do better than that, okay? Here are two orbits, for example. The red is one orbit and the blue is one orbit, okay? Now, you can see over here on the left side that this is, if I move it at, plot the position at regular time intervals, then you can see that here it is, the spacing is quite large, right? Spacing is quite large and here it is quite small. Whereas here it is sort of uniform, but gets squashed up at the edges over here, okay? So the red is reasonably symmetric, whereas the blue is not symmetric at all, okay? Now, so basically what is happening is that this is really an application of Kepler's laws, okay? Kepler's laws, because Kepler's laws tells you that it will sweep out equal areas in equal intervals of time, okay? For example, suppose I take this ellipse over here, okay? And I look at the semi-major axis A, the semi-minor axis A over here, and from the center over here, the distance to the focus is given by AE, where E is the eccentricity, which is square root of 1 minus b squared upon a squared. And the distance from the center to the focus over here is AE, which marks this is the focus of the one of the two foci of the ellipse over there. Now let's see what happens when you try to look at how the area gets chopped out. Now we want to find out which is the true focus of the eclipse about which the star is moving. Okay. Now if you look at the areas which are being swept out over here, okay, using this, you'll find that there is a variation as you start from the orbit and keep going further and further away. All right. Okay. Now you can see over here that you gather a large area. If you see over here, the area is very small. Just visually looking at it also, you can see that area is extremely small. And that area keeps increasing. It comes to a maximum over here. You can see this length is large, this radius is large, and then again, it'll keep small. So clearly this cannot be the focus at which this object is moving, because otherwise Kepler's laws would be violated. It cannot be sweeping out equal areas in equal intervals of time. But if you look at the other focus over here, okay, then you can find out that must be the true focus of the ellipse, because the area, this is the ideal case that I'm taking, is nearly constant, right? Because here the length is small, the angle is large. Here the length is large, the angle is small. So they compensate each other and give you a constant area as you would expect in Kepler's laws of motion. So what you try and do is that suppose you had an ellipse, okay? You had an ellipse, you play around with, you identify the right ellipse, you play around with the inclination angles, and you can try and see which gives you an answer in terms of obeying Kepler's law of sweeping out equal areas in equal intervals of time. So if you do that, you can see over here that this blue one corresponds to about 20 degrees. It's not perfect, but it is close, all right? But you can see that the other angles over there are much further off than than the blue one over there. So you can get a more exact value by trying to play around with the computer. And these computer simulations are now routine, so one doesn't have to rely entirely on the eclipsing binaries, which was traditionally what was used. Okay, it still continues to be used, of course, but you can see that you can also infer the inclination angle by doing the simulations of the orbits to obey Kepler's laws of motion. Now, Kepler's laws of motion have had widespread applications. I'll just show you two of them, and then we will close on the application of stellar masses, of applications of Kepler's laws in trying to estimate masses of objects. This was Andrea Ghez and Reinhard Genzel, who got a Nobel Prize in 2020 for estimating the mass of the supermassive black hole in the center of our galaxy. And this was nothing but applications of Kepler's laws. But as you can see, it is extremely challenging. It's extremely challenging because the movements right to the center of our galaxy are extremely small. So you need very high angular resolution observations, and you need to follow them year after year after year after year to try and get the motion, get an orbit, whatever it be, parabolic, hyperbolic, elliptical, and get an estimate for the mass of the supermassive black hole at the center. And animation, the stellar orbits in the center, 0.5 arc-second. Images taken from 1995 are used to track specific stars orbiting the proposed black hole in the center of the galaxy. These orbits and a simpler application of Kepler's laws provide the best evidence yet for a supermassive black hole, which has a mass which is close to about 4 million times the mass of our sun. And you can see SO2 over here. This particular star is particularly important because that has been tracked for one full orbital period. So you need technology, adaptive optics, which has been used, which we briefly mentioned while talking about optical telescopes, to correct for corrugations created by the atmosphere to try and get these very accurate masses of these objects of the center black hole. It just shows you the orbits as we keep going from here to here. This animation just gives you the motions of the stars. It's fantastic, actually, the kind of work they've done. Richly really deserved a Nobel Prize. And it's very painstaking work, not for year or two kind of thing. And they're following it for decades together, and to get an accurate estimate of the mass in the center of our black hole. This is just another animation of it, which of the inner motions of these stars. This is more in three-dimensional space rather than in 2 dimensions, as you saw earlier. The links are given over here, and I'll share the PDF files with you all, so you can look at these at your leisure as well. Okay, it's actually just beautiful watching this to see how painstakingly actually they have collected the information over years and years and years of very careful work to try and determine the motions of these stars and get an estimate of the mass of at the center of our black hole, at the center of our galaxy, as accurately as possible. Okay. Now, I'll just illustrate the Kepler's laws in one more instance, and then we will stop this estimation of masses using Kepler's laws. This is a nearby galaxy, and right in the center of the galaxy, what they have seen are maser emission. Maser emission, as you know, would occur in a particular spectral line. And so by looking at the Doppler shifts of the lines, you can estimate at what velocity these spots are moving. Okay. And with observations which have been done at radio wavelengths of very high angular resolutions, you can find out where these spots are located. All right. So this is an image right in the center of this galaxy. Okay. This is on the scale of milliarc seconds. Okay. Milliarc seconds would be, as we discussed earlier, what maybe a 5 rupee coin, somebody holds it up in Lal Killa in Delhi, you'll be able to say what the structure is from Pune or Bombay, right? So that is a kind of resolution that one is talking about. And then you can see that systematically, one set of maser spots are coming towards you and another set is going away from you. One set is red shifted, the other set is blue shifted. And they seem to lie on a slightly warped disk moving around the center over here. So using again, applying Kepler's laws, you know the distance, you know the velocity, okay? And the major spot masses are negligible compared to the mass of the central black hole. You can go and estimate the mass of the central black hole. This particular black hole is about an order of magnitude more massive than that of in the center of our own galaxy.